Well, our next speaker is very familiar to this podium and research presentations, and it's my privilege to introduce you Dr. Ali Pirasteh. His mentor is Takeshi Yoku, and Ali's talk is Inter-Method Reproducibility of Biexponential R2 Magnetic Resonance Relaxometry for Estimation of Liver Iron Concentration. And I said that all in one breath. Take over.
Thank you, Dr. Morris. Good afternoon. I have nothing to disclose. R2 MRI estimation of liver iron concentration is a very good surrogate for total body iron, and it guides the management of patients who have known or are at risk for iron overload. It's based on the principle that liver that is affected by iron overload loses signal on prolonged TEs compared to normal liver. And if somebody plots that signal against echo time, they can actually do a curve fit, and they can solve for R2. And if you solve for R2 and you get that for the liver, the average shows that correlates with liver iron concentration. And that's the basis for what is FerriScan Ry-relaxometry. It's a commercial product where you get spin echo images at 6, 9, 12, 15, and 18 milliseconds, put an ROI in the liver, and then it goes through this very complex post-processing that is done by Resonance Health. It's proprietary. It's very complex. At the end, the images are filtered. Then those ROIs are plotted against time. And then what they do is a biexponential fitting to the curve, which has a fast component by the red brackets and a slow component by the blue brackets. And then there's a weighted average to get the R2. Then they generate a pixel by pixel R2 map. And after that, that correlates with liver iron concentration. And this complex procedure is pretty much the only FDA-approved R2 relaxometry for liver iron concentration. However, what it lacks is independent validation by a third source, and nobody has been able to do this because it's so complex and it's proprietary until recently, where the Iron Man at our institution, with some funding from the Stark Industries, was actually able to reverse engineer this whole process. And thus, the purpose of this was to investigate the inter-method reproducibility of R2 MRI in liver iron concentration estimation in patients who have either known or suspected liver iron overload. Now, this was a retrospective analysis of the available imaging data. We included all patients who had known or suspected iron overload that had undergone a FerriScan protocol MRI. We acquired all the images on one of the 1.5 Tesla MR scanners at our institution, and all the images were obtained per the FerriScan protocol. Now, all images, the spin echo images that we obtained, they went off-site to Resonance Health for proprietary analysis. They did a simulated annealing curve fitting. That's what they do. And they generated an R2 map, and they gave us a proprietary R2. We took that report, same slice. We tried to replicate the same ROI as much as we could, and we did our own non-proprietary analysis and image post-processing. Then after that, we did one thing, a very similar simulated annealing curve fitting, as much as we could replicate it, generated an SAR2 map. Then we also did a good old-fashioned least squares curve fitting to get another R2 map. And then at the end, we also did a dictionary search curve fitting. And you might ask, well, what is this dictionary search curve fitting? If you imagine, it is difficult to fit a curve within these 5 data points, especially if you're trying to do a biexponential curve fit. If you normalize the signal, this has to fit within this equation. It has one coefficient of P in front of each component. It has an R2 fast component and an R2 slow component. The trick is to solve that. If the signal is normalized, all those 5 yellow lines are going to represent a unit vector with a length of 1. Then the trick is to find one of these curves that actually fits these 5 dots best. And each of these curves is represented by 5 signals, so S1, S2 through S5. And each of these in itself is a unit vector. So it's a needle in a haystack problem now. And the easiest way to match the yellow vector to one of these white vectors is to do simply a dot product. So you simply do a dot product. Since the length is 1, the one with the smallest theta actually matches. That would be the red arrow in the middle. You go back and look. That's the red curve to the left. You have your best fit. In theory, it should work. How do you feed this to a computer? Well, you tell a computer, I have a bunch of parameters, a P and an R2S and an R2F. You generate a matrix of how many ever variables that you would like with different intervals. Same thing with different echo times. And you have it do a dot product with the observed echoes that you got from the patient. That gives you a matrix of different numbers. The maximum, you can have the computer search for it, and that is the fit max, the largest number in there. You go back and see which parameters give you the maximum fit, and you have your R2S, P, and R2F. The weighted average gives you the R2. your R2 map that way. So we assessed the reproducibility using linearity and bias. The linearity was assessed by linear regression analysis, and the absolute agreement was with interclass coefficient and Blunt-Ullman analysis. We included all 40 MRIs that we had from 38 subjects. 2 subjects had 2 MRIs each. And the etiology of iron overload was pretty diverse, from primary hemochromatosis to thalassemia, hyperferritinemia of unknown etiology, sickle cell, or autoimmune hemolytic anemia. This is an example of the proprietary R2 by FerriScan, R2 maps by FerriScan. On the top, no significant iron overload. To the bottom, that patient has severe iron overload. I have the R2s and liver iron concentrations listed. Just for comparison, I have the R2 maps generated by us to the right of the dotted line. And the looks of the maps look fairly similar. If you compare the R2s across the board, they are also very similar, about 35 to 38 on the top row, about 110 to 118 in the middle, and 270, 280 at the bottom. How does this look across the population? Well, if we plot the FerriScan R2 against the, let's say, simulated annealing R2 on a logarithmic scale, the linear fit looks nice. The intercept is near 0, the slope is near 1, and it has a very good interclass coefficient and a good linear fit, 0.97 R squared. Can actually see a very similar thing when you look at the least squares R2 and also the dictionary search R2. They look near identical. We look for a bias. We did a Blunt-Ullman analysis. We have the difference in percent on the y-axis, the average on the x-axis, and there is no significant bias. Average is 0.18% with a p-value of 0.3. I'm sorry, the fonts are small. And the limits of agreement are about 7%. If you do the same thing with the least scores and the dictionary search, again, it's about 7 to 9%. That's where it is. And that's within what the FerriScan interscanner variability has been reported. It's about 9 to 10% for those guys. So in conclusion, we were able to observe excellent intermethod reproducibility of R2 MRI for liver iron concentration. This was the first successful replication of FerriScan results, and we did that by following the published general strategy by Sampier and Clark. This was despite the differences in code development, and it was seen across a wide range of liver iron concentrations, and we believe it speaks to the robustness of their general approach. There are limitations to this study. The sample size is small, the study is retrospective, and of course we have to take into account the differences in implementation of the FerriScan components. We just follow the general principles that they have described. The also thing to consider is there ROI colocalization variability from what we placed compared to what they placed? Is there intra-subject reproducibility? If you use a different slice for the same subject, is there going to be a difference? That's one thing that we're currently investigating. And also intra-observable reproducibility. If I do the ROIs versus the Ironman doing the ROIs, is there going to be a difference, or third person? So we're working on that. I'd like to acknowledge my mentors and a great team we're working with, also our excellent colleagues at the University of Wisconsin, Dr. Scott Reeder, Dr. Hernando, and thank you for your time.
Thank you very much. Dr. Linkinski.
So what's the rationale for biexponential decay?
As opposed to a monoexponential decay?
Yeah, I mean,
is that why we do a biexponential?
Yeah, now is there a physical rationale for thinking that it should be biexponential versus mono? I mean, it probably is biexponential, but depending on what the signal to noise is and whatever, you might not be able to tell the difference. And one of the problems is at the end of the day, they give you a weighted average of the two R2s, okay? And you could get lost in the shuffle by doing that. So it just would be interesting to know if anybody provides a rationale for doing biexponential.
So the rationale that they provide, the rationale that they provide. So if the paper that by Sampier and Clark, when they do a biexponential fit, they actually see a much better correlation with higher liver iron concentrations. As you go to higher liver iron concentration, when you do a monoexponential fit, the whole thing falls apart. The other thing is when you have when you have a liver that is very high in iron, you have a very rapid loss of signal. And at that point, doing a monoexponential fit, and we tried to do a monoexponential fit, and we actually were able to do that at 1.5, and there is bias. And as you get to the higher B values, it just doesn't correlate that well. So that is the rationale at this point. It's pretty much observant as opposed to other than that why. Exactly sure.
Takeshi.
The biexponential nature of the R2 decay has not been clearly elucidated, but the computer simulation suggests that the is due to two different species of iron-containing particles, ferritin and hemosiderin. They differ in the size and the magnetic effect, as well as the spatial distribution.
One more quick question. Ali, thank you very much.